Okay, welcome back to the Chemical Reactions Vodcast. This is Miss Carr, and today we're going to start by reviewing what we learned in Vodcast 1 about skeleton equations. So, we're going to practice writing a skeleton equation. This is one of those examples where I'm going to tell you to pause the video, and it's come to my attention after the last flip unit on moles that some of you guys aren't pausing the video. Pause the video when I ask you to, and make sure that you actually do these pieces of work. Now, the reason I ask you to do this is because in a classroom setting, I would certainly stop and have you guys work this. This is when I would make my way around to see if everybody's actually doing the work. Now, I trust that you guys will take the time to actually pause the video and do the work. The reason for this is that I want to make sure that you have it in your notes, and that if you made mistakes, I can see what those mistakes were when I make my way around to talking with each of you during your progress report. So please take a moment to read this equation and try to set it up as best you can before moving on with the video. So I'm going to go ahead and give you the equation in Word format. So I want you to take a second, pause the video right here, and try your best to set up the equation the best that you can. If you don't know what any part of it is, make sure that you circle it and mark it off to the side so that I can know where your stumbling points were. Okay, if you don't let me know where you're having problems, I won't know how to help you. So pause the video and work it out as best you can. All right, now we're going to take this piece by piece, and we have the solid glucose reacting with oxygen gas in the presence of heat to produce liquid dihydrogen monoxide and carbon dioxide gas. So hopefully you did at least get the majority of this question. If there were a few things that you stumbled on, that's fine. Because we are just practicing here. So I want to go ahead and start with our reactants. Okay, so what do we know is reacting? Well, we know that glucose is reacting with oxygen gas. Now remember, oxygen gas is a diatomic, so we're going to need to make that O2. Okay, in the presence of heat, so we know that we need to add that heat in there somehow to produce. So of course everything that's getting produced is a product. So we have liquid dihydrogen monoxide and carbon dioxide gas. So as we go through here, we need to find out that, or we need to put in our setup our glucose. That's C6H12O6. That's something that you should have committed to memory back in biology, because this is the sugar that produces all of the energy that our bodies need. So C6H12O6 is definitely one of those very important sugar molecules for you to memorize. And of course that glucose is in solid form, so we need to put the S behind it. And it is reacting with, so we need to add, that reacts with means a plus sign, with oxygen gas. Now remember that oxygen is diatomic, so we're going to put two of those oxygens in the presence of heat. Okay. We have the oxygen gas, sorry, in the presence of heat to produce. Okay. So the presence of heat means that we need to put that little delta. The way I always remember that when I was in chemistry is that it looks like a little campfire, right? So we're putting a little campfire above our reaction arrow. So they react to produce a liquid dihydrogen monoxide. So of course dihydrogen monoxide, also known as water, it's H2O, 2 hydrogens, 1 oxygen, as the name implies. And that is in liquid form, so we put the L behind it. And carbon dioxide gas. So we have the plus and then carbon dioxide, and it is in a gas form. So that is a skeleton equation. That is how you write it. You break down, remember, you should have noticed that every single word in this entire paragraph, okay, was somehow translated into something in this equation. Whether it is reacts with is this plus sign, the S is the solid, Okay, the C6H12O6 is the glucose. Okay, the reacts tells us that this is all on the left side of the equation. The presence of heat, it means that we have our little delta sign. To produce is the arrow. And then we have our liquid dihydrogen monoxide, and, which is our plus sign, carbon dioxide gas. So every single word in the equation or in the problem was important and should be paid attention to. So please keep that in mind. Okay. Now, today we are also going to talk about balancing chemical equations and how we use these skeleton equations to produce balanced or correct chemical equations. So let's look at the equation that, say, for example, that you need to make bicycles. Okay, we're going to keep it simple. So to make a bicycle, you have a part. You have 4 different parts. You have frames, wheels, pedals, and handlebars. So the skeleton equation would look like this. It'd be a frame plus wheel plus pedal plus handlebar equals bicycle. So this would mean that these things could react together to produce a bicycle, or could be placed together to produce bicycle. Now the problem is this equation isn't really complete. It's the skeleton. It is all of the parts that make a bicycle, but it's incomplete because the ratios aren't correct. If I were to give you a frame, a wheel, a pedal, and a handlebar, you wouldn't be able to make a bicycle out of that. So the ratios of the reactants aren't correct here. What we would need to do is we would need to add a number called a coefficient. Now, coefficients are numbers that come in front of each of the elements in a chemical equation. So these coefficients would need to be put in front of, in our example, the wheel and the pedal, to indicate the correct number of parts that we need. So if we were to balance this equation for the bicycle, we would need 1 frame, 2 wheels, 2 pedals, 1 handlebar in order to make a bicycle. So this is the balanced equation. Okay, so remember, the skeleton equation is just all the parts. The balanced equation is how many of each part you're going to need. Okay. So also note that you don't need to add the number 1 in front of the frame or the handlebar, because that's understood. Remember how chemists hate the number 1. We don't want to use it if we don't have to. So we leave the 1 out of the frame and the handlebar because it's understood that we're only dealing with 1 of each. Okay. So you could put this into symbol form. You could have the frame is the symbol F, the wheels are the symbol W, the pedals are the symbol P, and the handlebar is the symbol H. So you put the frame, 2 wheels, 2 pedals, and handlebars together to produce this compound, which of course would be our bicycle. So we have a very clear understanding, hopefully, that the only reason that we really need to balance chemical equations is to make sure that those ratios are correct. Okay. So you might be asking yourself, like, why would we need to balance those chemical reactions? Okay, and we have a crazy doctor looking lady here to tell us exactly why. And the reason is the law of conservation of mass. You guys probably learned about this back in your physical science days, probably 7th or 8th grade. And the law of conservation of mass says that matter cannot be created or destroyed. And so you can't get out of an equation more than you put into it. So the number of atoms of each element that we start with must be equal to the number of atoms of each element at the end. So if we look at the number of atoms or elements in the reactants, they must equal the number of elements in the product. And that is because of the law of conservation of mass, because we can't make a hydrogen atom out of nothing. We have to bring that hydrogen atom in from somewhere else. Okay. Now there are some basic rules of balancing equations. These are definitely things that you do want to include in your notes. Okay. The first is that you write the correct skeleton equation. If your skeleton equation is wrong, your balanced equation will also be wrong. So this is where knowing your nomenclature becomes of the utmost importance. And I've been trying to stress to you guys the importance of knowing your nomenclature from the very beginning of the school year, but this is where the rubber meets the road. If you can't get your skeleton equation right, your entire balancing equation is going to be off the rails. So we need to make sure that you do write the correct skeleton equation. The second part is that you need to count the number of atoms in each element of the reactant. So on the left side of your chemical equation, you are going to count the number of atoms of each element. So I need to know how many hydrogens, how many carbons, how many oxygens, how many nitrogens, and count them all up. Okay? Then you want to count the number of the atoms of each element of the product. So on the right side, you want to do the same thing. You want to count how many hydrogens, how many carbons, how many oxygens, how many nitrogens, how many of what do you have on that side. Okay. So in both steps 2 and 3, remember that if you have a polyatomic on the reactant side, you don't want to separate those elements on your product side. So your polyatomic as an ion is going to stay together. That polyatomic's not going to break apart. So if you have something like sulfate on the left, it's going to be sulfate on the right as well. So you're not going to break up that sulfur and oxygen. All right, then you balance the elements one at a time by changing the coefficients. You never change the subscripts, okay? So if you have O2, it better stay O2. But you can change how many O2s you have. And you may need to go back and forth several times, okay? So let's give this a try, and I'll walk you through it the first time, and then I'll give you an opportunity to try it on your own. Okay, so we have hydrogen plus oxygen produces water. So the first step, of course, is that we wrote the correct skeleton equation. We have the right elements on the left and the right elements on the right. And I should say the correct elements on both sides. So then you can draw a line to separate your reactants from your products and total up your hydrogens. We have 2 hydrogens over on this side, and we have 2 oxygens over on this side as well. Okay, and on the product side, we have 2 hydrogens and we have 1 oxygen. Now, this poses a problem because now we have an unbalanced equation. Somewhere we lost one of those hydrogen atoms. And if matter can't be created or destroyed, that hydrogen, somewhere it got destroyed. So we need to make sure that we balance it so that this doesn't happen. Okay? So we want to make sure that we have 2 oxygens on this side, on the product side. So we add a 2 in front of the H2O, because remember, we cannot change the subscripts. We can only change the number in front of that molecule. So over here we have 2 H2O, which is going to change the number of our atoms. So we change the total of our atoms to the number of H's to 4 and the number of O's to 2. Okay. The next step here would be to make sure that we come over here and make sure to balance it, to make it fit. So here we had 2 H's and 2 O's, but then by putting the 2 coefficient here, we have 4 H's and 2 O's. And if you look on the reactant side and your product side here, you see that our equation has balanced. Okay. So this is how equations are balanced. Now I'm going to give you a few tips and tricks on how you can make this work fairly easily every time. Okay, but I want to do one more example, and I want to give you a chance to set this up, and then because I want you to actually work the problem, I'm not going to walk through it with you, but I will walk through it with you during the next Vodcast. So this is going to be an example that I'm going to give you guys as homework. So put this in your notes, do the best that you can, and you can use your periodic table and your star reference materials to set this up. So your example here is silver 1 nitrate reacts with copper metal to produce copper 2 nitrate and solid silver. So give that one your best shot and mark down any problems that you're having with it. Please be as specific as you can. If you just come to me and say, I don't know what to do here, then I'm not sure where to start with you. but if you can tell me exactly what your problem is, I'll be happy to help.